Thanks for the follow, Eshkatan. I'm sorry that happened. Sometimes my stream just kind of dies. Thank you so much for the follow, homie. Welcome to the channel. Stream do be dying, though. Let me refresh on this end. Okay. Sorry about that, everybody. Hopefully everybody's not gone. That would make me sad. Dubs. No dubs. Okay. Called a Sonar Transducer, it's located below the waterline of an attacking ship. It transmits sound waves which reflect back to the ship after hitting an underwater object. By measuring the time required for the sound waves to reach the target and return, it is possible to determine the range. Bearing is the direction from which the waves are reflected. Target course and speed can be calculated by observing changes in range and bearing. Once the above factors are known, it is necessary to determine one's own ship's course, and the proper time for firing, as opposed to gun elevation and train orders required for surface and anti-aircraft fire control. Because you gotta point the ship at the submarine most of the time, at the very least. Welcome back, everybody. I'm sorry about that. Why'd that last sip of Coke taste like Old Bay? Not that I'm complaining, but it's a very weird taste. Adjust my pantaloons. Oh, goodness me. Thank you so much for the follow. Stream did die there. Seems to be a problem we've been having lately. Only with Twitch. I don't disconnect from Discord calls or anything, so I don't exactly know what's up. We're in an OBS problem, I guess. Let's see, where were we? Once the above, okay, we already said that. A survey of anti-submarine fire control systems. The anti-submarine fire control system on board the general-purpose destroyer, the most common non-specialized submarine fighter, normally consists of the following units. 1. The sonar equipment, which transmits and receives the sound waves to locate the target. 2. The sonar range recorder, which automatically records the range received from the sonar equipment and passes that information on to 3. The attack director, which also receives target bearing information from the sonar, ship's bearing from the gyro, and ship speed from the pedometer log. The attack director's job is to solve the fire control problem, that is, determine ship's attack course and time to fire. There's the sonar, which is a little nub. It changes form depending on which sonar it is and what ship it's on. But generally it's a nub. Sometimes they're retractable, which is kind of crazy. I believe this is a retractable model. The attack bladder displays on a screen a picture of the movement of own target and own ship and target, and may be used to solve the fire control problem graphically in case of failure of the attack director. By then it means say, hey, we got to turn the ship a little. The other thing's shot. It doesn't work. We can turn and we can do this the manual way with this fun little picture. There's a lot going on here. But it works. It works, okay? You'll learn more about these components and their operation a little later. A survey of torpedo fire control systems. The torpedo is recognized as the most effective underwater weapon of naval warfare. It may be of the homing or non-homing type. Homing torpedoes can detect sound of a ship's rudder or engines or whatever, or propellers churning the water, or it could detect metal and electric stuff, like a sea mine would. Our discussion here will pertain only to the non-homing type. Torpedoes may be fired from submarines, aircraft, or surface vessels, for each of which the torpedo fire control problem is quite different. When firing torpedoes from aircraft, submarines, or PT boats, it is necessary to have the ship pointed at least in the general direction of the target. A destroyer, however, is equipped with torpedo tubes that can be trained to aim at the target, as in they rotate in a circle, or a half circle. Ooh. You're getting free burps tonight. Two kinds of control are used for destroyer torpedo fire. One, bridge control, the primary method of control in modern destroyers, which is remote control from directors. And two, local control, in which the proper settings are made at each mount by means of the torpedo tube mount site, which the director control system is when the director control system is inoperative. The primary function of the torpedo director is to control the tube mounts by electrically indicating to them the proper settings to obtain the desired torpedo course for scoring a hit. Again, math. This is bit easy. This is simpler math, slightly, than I'll actually do a diagram. I don't know if is there a diagram of how torpedoes work? No. Okay, not yet at least. But I'm gonna make a diagram for you guys. So give me a second. OBS. I'm going to select this to paint for a second and then bring it back. Okay. So this is ship 1. And it's running parallel to ship 2. They're both moving at different speeds. This one's going a little bit fast, or a little bit slower, or a little bit faster, sure. So when you're aiming the torpedoes, you don't want to aim at the guy because the torpedoes move at roughly the same speed of the ship or a little bit faster. And by the time that they get over here, right, then it's not going to be there in time. So this is a simpler math because it's just trigonometry for the most part, if ships are moving totally straight. So the torpedoes would be aimed ahead so that they arrive at the point that the ship will be. I guess this kind of is the point for most weapons involved in this manual, but yeah. I don't know, I wanted to draw stuff. Let me go back. And then bring this back. Congratulations. Let me check my computer book. My computer book. Twitter notifications? Nope, that's okay. Well, posture check. Okay, buddy. Posture status checked. It is done. I'm sitting upright. So there's like a seat on the destroyer tubes. It looks really weird. If like you visit a destroyer museum and you see this, oh, where's my mouse? Let's get the mouse in here. But like these guys here, it looks a little bit weird at like a museum because there's nobody sitting there, you know, doing the thing. But it's a seat with a sight for local control. In the case of this director, doesn't work. This thing just says like trigonometry or whatever. Destroyers usually fire their torpedoes in a spread to increase the chances of scoring a hit on an enemy who's probably aware that he's being attacked and therefore taking evasive action. You will learn more about the use and control of torpedoes later on. A survey of rocket and guided missile fire control methods. Short-range barrage rockets have proved to be an effective weapon in shore bombardments. The principal ship used to fire rockets is the LSMR, which is the landing ship M medium rocket. I think the M is medium, which mounts 10 rocket launcher assemblies. Any one or all of these launchers. Actually, I'm going to pull up a video. You guys get a video. Give me a second. This is a special treat. Yeah, it is medium. Okay. So this ship is firing a couple rockets. This is not the same ship that I'm talking about here. But we will see it. Here's some recordings. Get some ships sailing around. Let's skip to the juicy bit, though. So they're firing off rockets. You see them fly through the air there. Real light. Where's the big boy? Where's the big one now? Is this one of the crazy one? No, this isn't the crazy one. This? Training film.
A gunboat is a word for it.
I hope that wasn't too loud. Something weird was
And take comfort in the thought that it's built to fill those 5, 10, or 20 minutes with a hurricane of light and heavy automatic...
Loud? Okay, I don't know what's going on, but I'll fix it. I'm sorry. Director control. Here we go. Here we go. Watch this. It's crazy. His videos really fired like 20, but I can't find it, it seems. Yeah, I don't know what that was about. One of my plugins is weird, I think. But that's alright. Probably. LSMR, which launches 10 rocket assemblies. Any one or all of these launchers may be controlled by either of two duplicate rocket fire control systems. Each system includes a gun director, a stable element, a gun order corrector, and auxiliary components, all of which were developed for the control of conventional guns but have been successfully converted to the control of rocket launchers. A rocket isn't that much different from a naval shell. It follows an arc, although its propulsion is a little bit different, obviously. It still moves in an arc, so it's ballistically calculable. The conventional projectile fired from a gun, or the barrage rocket, is committed to a given course at the time of firing. The target may change course or speed during the time of the projectile's flight, in which case the result is a miss. A guided missile, however, is subject to control so that it will alter course after launching to score a hit regardless of the target's evasive tactics. In order to control such a missile, it is necessary to know the relative positions of missile and target at all times, and to be able to effect appropriate alterations to the missile's course from a remote position. To accomplish this, guided missile fire control systems include components carried by the missile, which receive and carry out directions received from the radar and computing equipment on the ground. So this is anti-air guided missile, AAGM. The computer's telling it where it will be, and it points it at it. And here you see the classic shape, the triangle. What a useful shape. How you are going to learn. You will learn. On the preceding sheets, you read about the history of guns and fire control devices. You learned about the main components of fire control systems, and you took a quick look at some of its specialized applications in anti-aircraft, anti-submarine, torpedo, and rocket, and guided missile fire control systems. In continuing your study of fire control fundamentals, you will learn about the theory of guns and ballistics. What happens to a projectile while in the gun and during flight? Then you will go deeper into the basic fire control problem, that of hitting a moving target from a moving ship. You will learn more about the various components of fire control system, how they perform their jobs, and their applications in surface, anti-aircraft, anti-submarine, torpedo, rocket, and guided missile fire control systems. Ooh. Finally, you will be given an introduction to some of the Navy's special equipment used in fire control devices, including radar, sonar, synchros, and servos. You gotta use Yu-Gi-Oh monsters, bro. You'll learn about these things by studying these information instruction sheets and discussing what you read with your instructor and your classmates. You'll be given plenty of opportunity to ask questions and make comments about what you read. If something is not clear to you, ask about it, because there is much to be learned and it is important that you fully understand each lesson before proceeding to the next. Bro, out here giving a full seminar on boats. You bet I am. Specifically fire control. A very important part to the boat. Probably one of the cooler jobs to have. Depending on what you find cool. Being the guy who points him at a guy and clicks the blow this person up button is... that's a pretty cool job, I think. To have. That dude looks like how you feel. Reading. Turn this into a reaction image. Just crop this in like a... I'm not doing it because it's going to blast your ears. Blast you? Let me see if I can lessen the blasting. This kills the music volume, but... Okay, hopefully it wasn't that loud. Let me get into Discord over here. Okay, it's in the meme channel on my Discord server. If you guys aren't people need waking, sleeping in class. You guys better not be watching my stream in class. So here, if you guys aren't in my Discord server and you want to get in, there you go. What does that sound? Hi, helicopter. Now that you know what and how you're going to study, let's get started by reading about guns and interior ballistics. Thank you, helicopter. Next part. Whoa. Isn't this a cool graphic? It's a lot better than those PowerPoints that Atropa would talk about. She said she went to PowerPoint hell. I think manuals are a lot better than PowerPoints. What do you guys think? It's at your own pace. You don't have to take it at the pace of the instructor. It tells you all the information straight up. You don't need to take notes, really. This is where most of the fun graphics that I've posted on the internet have come from, this part. I'm going to actually check the internet first. Okay. I have 2 notifications. Thank you for the likes on Twitter, Eshkachan. I will follow you shortly, just so you know, after the stream, because I'm based like that. I follow people back as much as I can. What do you know about guns and interior ballistics? As a fire control technician, you will not be concerned directly with your ship's armament. You will not be called upon to maintain or repair the guns themselves. Hydrate. Okay, I'm gonna have to get up. You made me get up. I'm gonna have to click the BRB. I'll be right back. I haven't used the screen in a while. Let me get my keys. I'll be right back. Get some water this time instead of Coca-Cola. Whoa, almost fell. Enjoy the lo-fi. Hello, I'm back. I'm back. I'm back. I'm back. I got my water and my big old cup. Man, oh man, is this a big cup. Say anywhere, I've looked before, but I didn't want to make a mess. But I'm less afraid of making a mess now than I was before. No, it does not say. It doesn't say. But welcome everyone to stream. I see my viewer count went up. Welcome. We're still reading the manual. We're at the second part of like 8. This is a really long manual. I don't think I'll be able to do the whole thing this stream. Though I'll certainly try. I will certainly try. 1 second. Ooh. Took a while to fade in. You guys saw some clapping. Ooh, okay. Now I'm going to take a sippy. There you go. I hope you heard that sipping. Like a nasty noise. Actually, I gotta check my phone. Just a second. Just a second. Okay. However, a ship's armament would be useless without an effective fire control system, and vice versa, so you should know something about how and why the guns on your ship work. Fire control equipment. Plus the ship's gun, make a team. Thanks, fire control. 2 very important elements of the fire control problem are projectiles' initial speed and direction. You are indeed, therefore, in gunpowder, guns, and interior ballistics to the extent you're interested, therefore, to the extent that you should become familiar with the factors which give a projectile its initial speed and direction. The purpose of this section of instruction sheets is to tell you all you need to know about guns and interior ballistics. You're not expected to be a ballistics expert or an ordnance designer after you finish reading this section. For those subjects are major studies in themselves. A general understanding of basic theory, gun construction, and familiarization with the terminology is all that is required. Okay, let me move my phone so I get less distracted. Okay, gun construction. A gun is a tube. There you go, fellas. Capable of containing and controlling the explosion of a propelling gunpowder charge so as to discharge the projectile at a high velocity. The caliber of a gun is the inside diameter of its bore in inches or millimeters. So it's 3 inches at the thinnest. So that's its bore. It's a 3-inch gun. And it is 50 calibers, as in 150 inches. Ooh. All guns of 3-inch caliber and above have their length expressed in calibers immediately following the bore designation. This is the case for the US Navy specifically. Other navies don't always do this. The Japanese, I believe, used the full designation. I believe. Some countries would have. Probably the Germans. Yeah, the Germans definitely would have used the full designation for smaller guns. Following the bore designation, a 3-inch 50 caliber gun has a 3-inch bore and is 50 calibers, 150 inches long. Guns used aboard Navy ships range in sizes from 16-inch/50 caliber guns on battleships, which can fire a projectile more than 15 miles, to 20mm automatic anti-aircraft guns used aboard all Navy ships. Though these guns vary greatly in size and operation, their basic components are essentially the same. The major parts of a gun are illustrated below. Here you see recoil mechanisms, which help to make the gun not go flying backwards and it explodes like 50 pounds of explosives go off in it so that you can shoot the bullet out, the projectile out. The breech where shells go in. The yoke, I don't remember what the yoke is, but it'll describe it. And the barrel. Ooh. The breech is the rear end of the gun, into which the projectile and propelling charge are loaded. Wait, what was that? Okay. The barrel is the tube through which the projectile travels after the propelling charge is fired, and which gives the projectile its initial direction. The yoke connects the barrel and the breech to the recoil mechanism. Okay, got it. Part of the recoil mechanism may be mounted on the gun. The recoil mechanism is primarily a part of the gun mount, which will be discussed later. Guns are classified according to bore diameters. 1. Major caliber, 8 inches or larger. 2. Intermediate caliber, greater than 4 inches and less than 8 inches. And minor caliber, greater than 0.6 inches, but not more than 44 inches. 0.6 inches. It's like 13 mil. For small arms, 0.6 inch or smaller. We will not discuss small arms in these sheets because their fire control system are simply sharp eyes and steady hands. Okay, we're getting into some actual ballistics here. The bore of a gun is the interior of the barrel. It is uniform in diameter and extends from the chamber, which receives the projectile and propelling charge during loading, to the muzzle of the gun. The bore is rifled, which means that a series of twisted grooves are cut on its surface. The rifling imparts a spin to the projectile as it travels through the bore, and this spinning motion prevents the projectile from tumbling after it leaves the muzzle. You learn more about this tumbling action when you study exterior ballistics. This is important. For all of us boys out there, this happens when we pee. Us men are rifled, as far as I can tell. I could probably double check, but I won't do it on this window at the very least. But I am very confident that us men pee is rifled, and that's what kind of comes out spin. Okay. In order for a gun to discharge a projectile at high velocity, the force resulting from the explosion of the propelling charge must be exerted on the rear of the projectile. To accomplish this, guns are equipped with breech mechanisms which seal the breech of the gun during firing, but which can be opened to allow reloading. Usually they kind of lock in place, like a bank safe. It's very tightly shut. Breech mechanisms may be very simple, as on a single-shot rifle, or very complex as on an 18-inch gun, but they always serve the function of sealing the rear end of the gun tube during firing. Gun mounts and turrets. Guns must be mounted aboard ships in such a manner that they can be rotated horizontally, trained, and vertically elevated. By means of these two motions, a gun can be pointed in any direction. As you can see, this is how elevation and train works. It goes in circle for training, and up and down for elevation. This is a 3-inch 50... Actually, no, it isn't. This is the 5-inch mount, I think. Just without the other stuff on it. The mechanism which supports the gun and moves it in elevation and train is called the gun mount. The major components of a typical gun mount are the elevating mechanism, the traversing mechanism, the recoil mechanism, the trunnions, the carriage, and the stand. Stand? Dude, is that a JoJo's reference? Holy crap. Oh my god. These are good beats, by the way. Thanks, Twitch. Let's see, so here you see all the bits. The elevating mechanism may be power or hand driven and moves the gun in elevation. The traversing mechanism, also power or manually operated, trains the weapon. The recoil mechanism absorbs the forces resulting from the explosion of the propelling charge and allows the gun to recoil, move to the rear. The stand supports the entire gun and mount and is rigidly attached to the deck. The carriage rests and rotates on the stand so that the weapon can be traversed. The trunnions provide a pivot support between gun and carriage so that the gun can be elevated. Continued. Most major caliber guns, 8 inches or up, are mounted in heavily armored structures called turrets. Intermediate caliber guns, over 4 inches and less than 8, are mounted in unarmored gun houses or are provided with shields. Minor caliber guns are shielded or simply mounted in the open. A turret performs the same functions and has the same major components as the gun mounts discussed on the previous sheet. A turret differs from an ordinary mount in that it is heavily armored and fully enclosed. 2 or 3 guns of 8-inch caliber or larger are mounted in a single turret. The major components of a gun turret are shown below, with the names of the equivalent mount parts indicated. Ugh. So here you can see carriage, barbette, which is the armor around the turret, all the mechanical stuff on the inside that I don't think are discussed in this, but they might be. And then the gun house, which has all the bits that we talked about earlier on this page. The rollers allow the gun girder. Rollers are a bunch of balls and stuff that help it spin. Gun girder to traverse on the turret foundation and stand. The gun house provides armor protection for the gun crew, and the heavy armor of the barbette protects the lower turret components. Gun mounts and turrets differ wildly in complexity and type, depending on the size, type, and number of guns mounted. It is hard to compare the free-swinging mount of the 20mm anti-aircraft gun, which has no elevating or traversing mechanisms, to the massive and intricate 16-inch gun turret, but they all serve the same basic function: to position the gun in accordance with fire control directions so that the projectile will hit the target. So here we see different propelling forces. Something goes boom, it pushes bullet out, projectile, shell. What's the word? Oh, I forget because it's been a while since I've done any kind of science stuff. Potential energy is in the case of the bow and arrow, and the rubber band on the slingshot, the force at play. It's a bit different than explosive force, I think, but it's the same idea. In order for a projectile to be fired from a weapon, it is necessary that a force be exerted on the rear of the projectile. The stretched rubber band of the slingshot supplies the propelling force to a stone. The taut string of a bow exerts the force necessary to launch an arrow toward the target. In a similar way, an explosion, rapid burning, which that's what an explosion is, by the way, folks, of gunpowder in a gun generates hot gases which expand and exert tremendous force on the rear of the projectile to propel it out of the gun. Gunpowder is a term applied to a family of explosive substances which, when ignited, burn very rapidly, liberating large volumes of high-temperature gases which create very high pressures. If this pressure is confined in a gun barrel, it will exert a great force on a projectile contained in the tube, forcing the projectile out of the gun at high velocity. When the projectile hits the target, the explosive within the projectile is set off. The resulting explosion and damage to enemy ships or aircraft is the only reason for carrying guns and fire control equipment on Navy ships. There are two general types of explosives, called low explosives to fire the projectile from the gun, and high explosives, used as bursting charges within projectiles or mines, torpedoes, etc. to destroy or damage the target. So low makes go out, high makes stuff go boom. Characteristics of explosives. Continued. The difference between low and high explosives is primarily in the rate at which the explosive burns. A low explosive has a relatively slow burning rate, and thus generates pressure within a confined space more slowly than does a high explosive, which reacts almost instantaneously. A high explosive is desirable for inflicting a maximum amount of damage on the enemy, but if used as a propelling charge, would probably destroy the gun in which it was used. The reason for this is shown in the graph below, which indicates the pressure generated within a gun barrel by both types of explosive as the projectile is fired. The high explosive would create an initial pressure which would exceed that which the gun can withstand. Oh my lord. Oh my lord. If the pressure inside the gun is too high, it goes boom. And you don't want the gun exploding on you. That's bad. So you want to use low explosives in high quantity instead of a medium quantity of high explosive. So here's the graph. And also low explosive it doesn't go off as fast. Of course, this is all occurring within like the span of like a tenth of a second, right? But it goes for longer, which means it pushes longer through the barrel, which is important. I think it might discuss that. Both high and low explosives require the application of some form of energy to initiate their explosive reaction. This initiation is supplied by heat for low explosives and by shock for high explosives. This initiating energy is supplied by a small charge of initiating explosive, a very sensitive high explosive which produces both a flame and a shock when set off by being struck sharply. Ammunition and projectiles. Ammunition is the name given to the group of components which make up a complete charge or round for a gun. These components are 1. The primer, 2. The propelling charge, 3. The projectile, and 4. The fuse. This is the case for every kind of bullet, basically. Well, in cases of most bullets, there isn't high explosive. And bullets with high explosive, it tends to be in the bullet part, I believe. But the idea still stands. So this is a diagram of the 3-inch 50. This is what the ammunition generally looks like on the inside. And the fuse can be rather complex. Like there is a VT fuse, which I might mention. The primer, which is this thing here, contains a small charge of initiating explosive which, when activated by the firing mechanism of the gun, sets off the propelling charge and fires the gun. The projectile is the payoff, the missile which is fired at the target. The fuse is fastened to the projectile and sets off the high explosive projectile charge when the projectile strikes or approaches the target, depending on the type of fuse used. Ammunition may be of a fixed, semi-fixed, or bag type. Fixed ammunition has all of its components assembled in one unit with the primer or propelling charge contained in a cartridge case which is attached to the projectile. This type of round is illustrated above and is used for all automatic guns from 20mm through 3-inch. It is necessary that automatic guns use fixed ammunition in order that they may be loaded rapidly by means of automatic equipment. After each round is fired, the empty cartridge case is automatically ejected from the gun. In semi-fixed, here's a diagram of semi-fixed ammunition, the primer and propelling charge are contained in one unit, and the projectile and fuse make a separate unit. This type of ammunition is used in 5-inch, 6-inch, and some 8-inch guns. The need for loading each of the two units separately does not make this type of ammunition suitable for automatic weapons. Part of why this is used is because if the primer and the propelling charge for a 5-inch shell was included, it would be really heavy and you wouldn't be able to fire fast enough. The loaders wouldn't be able to do it fast enough, but in 2 pieces, it's a lot quicker. Because the 5-inch shell already weighs like 50 pounds, I believe. And yeah, I think it's 50 pounds. And you don't really want to be adding another 50 pounds on that. You're going to get exhausted quickly for one. So they have 2 different parts. The third type of ammunition, which is used in some 8-inch guns and all guns larger than 8 inches, is bag ammunition. In this case, the primer is separate from the propelling charge so that the round is loaded as 3 separate units. The primer is inserted into the firing mechanism of the gun rather than being built into the case of the propelling charge. It kind of looks like this. This is a very weird looking 16-inch gun projectile. I'm not sure what it's supposed to be. There's a tiny little baby primer. And usually there's more than one bag. It's not just this. If you look at a video of the Iowa's loading, which actually I might pull up. Give me just a second. Hide Vivaldi. Because why not just show you guys straight up?
The 16-inch guns on the Iowa-class battleship are a marvel of engineering and firepower, able to...
Is this the video I want? No, I wanted like an actual video. Here we go. Let me turn off the music.
Right gun is ready. Left gun is ready. Copy that.
Is this too loud? Is this what I'm looking for? That sound as though the barrel's being cleaned from any powder and residue that's left behind after firing. Here's the loading. Give me the loading video. Okay, we're gonna go with this. Let's go with this. Oh no, it's left side only. This is a shaky video from like Desert Storm, so. It really is only the left audio channel. It sucks. Let's see the loading. God, this is a bad video. Okay, let's just go to the Navy one. Let's go with the Navy's video from 1955.
Moving to the powder hoists. And the car starts up.
So they send stuff up from the magazines
It's easy to
and
see
inside the barbette.
working with only the crew of a single gun.
Here we go.
Each gun crew consists
So there's the gun, there's the breech block.
of a cradle operator, a rammer operator, and finally a primer man.
These turrets are huge, by the way, on the inside.
As soon as the projectile arrives at the top of the hoist, it stops in the cradle.
This weighs 2,700 pounds.
Guns, loading can be accomplished at any angle of elevation. But these big 16-inch guns must be brought to 5 degrees elevation. When the gun is in loading position, the gun captain opens the breech. Then the cradle and spanning tray can be
I think this should be a little bit louder.
cylinder to align with the bore of the gun. When the spanning tray is in position,
How's that
the
sound?
rammer operator rams the projectile into
Projectile is rammed up the gun.
the rammer is retracted, and the gun is ready for the powder bags. Now the powder trunk door is opened, and
It's kept closed so that if there's an explosion, it doesn't get set off.
Then the powder car moves down, and 3 more bags are rolled into the tray. All 6 bags are now rammed slowly into the gun.
Those are dropped right next to where they
Right,
get
6 bags,
it's loaded.
each one about 18 inches long and 18 inches in diameter. The rammer is retracted. Now the cradle operator raises the cradle and turns the ready switch to ready. The gun automatically goes back to firing position, and the firing circuit can be completed. The return of the gun to firing position automatically flashes a gun ready signal to the turret officer's control panel, and the gun is ready for firing. When the recoil and counter-recoil action are complete, the gun returns to the loading position automatically. When the gun captain begins to open the breech, the gas ejection system automatically blows the bore clean of gas or any burning fragments. Now the gun is ready for the next round, and the cycle starts again. Of course, all you've seen are the actual steps required to load and fire only one gun. Now, when you multiply that by 3, and you want to keep them firing, there's a lot more that goes on. Not 4, but 13 men are handling powder. Not 4, but 15 men operating each projectile flat, and both flats being used. Then there are 4 men on the machinery floor, 3 powder hoist operators, 12 men working...
It's a big job. It takes a lot of people.
6 at the sight stations, and 8 men in the turret officer's booth. A lot of men. But as we said in the beginning, it's a lot of turret, too. As a heavy bombardment weapon against shore installations as much as 20 miles inland, the 16-inch gun is a valuable and accurate weapon. Even under ideal circumstances, you could see only about 14 miles from the deck of a battleship. But with these ships 20 miles apart, it's possible to land a salvo of 16-inch projectiles accurately on the target.
Over the horizon.
Although firing, of course, can be directed from each turret individually, gun laying and firing is usually accomplished from remotely located directors operating.
Yeah, it's the same principles that we've talked about so far. And it's the loading process if you didn't know. I thought that was a cool little video. Let's get the music back. Hopefully the audio was good there. It might have been quiet at the start. There we go. We got our lo-fi back. Let's turn the lo-fi down a little. It's a bit loud. Now it's a bit quiet. Let's go around there. Okay. What do you guys think about that? I'm going to check computer things. I got a reply on a on a tweet I made by a boat historian. Based. Me identifying a destroyer. What's my phone lighting up for? Okay. Did I make it all the way loud? No. The propelling charge of bag ammunition is contained in raw silk bags, which burn completely during firing and leave no residue. The number of bags of propelling charge used to fire a projectile depends on the particular gun used and the range desired. So you can use a half charge if you don't want to fire laser beams out of your gun at short range, and you want to go for a diving shot for some strange, bizarre reason. So you're probably going to be less effective when you're doing that, but it's more used for like short bombardment, I'm pretty sure, that you do that. You usually want full salvos for naval engagements. Hopper. The projectiles used in a given gun vary considerably depending on the purpose for which they are used. Shown below are 5 different types of projectiles, each designed to serve a particular function. Several elements of various types, however, are common to all. The rotating band, which engages the rifling of the bore as a projectile travels through the gun tube, keeps propelling gases from escaping past the projectile, and gives the projectile a spinning motion, is common to all types. The projectile body in all types serves as a base to which all other projectile elements are attached. Ooh. So here we see the bits of various parts. The dummy round is full of sand so that it has the right kind of weight. And a plug instead of a proper fuse. Armor piercing has a tracer. That's not for every single kind of armor piercing thing. That's more for like actual bullets. I don't believe there are tracers in most 8-inch shells or anything. There might be color splashes, but that's a whole nother thing. I don't know if there's any video color splashes in use. I don't think that many people other than the Japanese use them a lot. And the British maybe. Where when the shell hit the water, it would release dye as it exploded. So that if it went off, there'd be like a red plume, and you know which shell fired that shot. It was a pretty cool system, I think. If multiple ships were firing on the same target at the same time. Ooh. The common anti-aircraft projectile is used against air targets. It uses either a time fuse, which explodes a charge at a preset length of time after firing. This is done via math. Like you figure out where it's going to be, the aircraft is going to be, and you fire it to where it'll be. But you're also going to have to calculate when it'll be there, so you know how long in the air it would be. So you can explode at the right time. Or proximity, aka VT fuse, which functions when the projectile comes within a certain distance of the target. The common projectile uses a windshield to reduce air resistance during flight and is used against surface targets. And the illuminating projectile uses a time fuse and contains an illuminant, which gives off intense light when the projectile burns, illuminating a large area. This is for nighttime if you need visual spotting. It's most useful, I think, in 1953 for helping people on land if you're assisting in like a landing operation or something, because radar is going to do all that work for you most of the time by that point at night. The armor-piercing projectile has a hardened steel cap to penetrate armor before exploding. The target projectile has no explosive refuse and is only used for target practice. Tracers, which burn during flight so the gunner can observe the flight of the projectile, are provided in the base of many projectiles. The meaning of interior ballistics. The term ballistics was derived from ballista, which was the name applied to an ancient weapon used for hurling large stones or other missiles against fortifications. Today, ballistics means the study of the motion of a projectile from the time the propelling charge is ignited until the projectile hits the target. Interior ballistics is the study of what happens while the projectile travels through the bore of the gun from the instant of firing until it leaves the muzzle of the gun. Exterior ballistics refers to the action of the projectile during its flight from gun muzzle to target and to the factors affecting its travel. As a fire control technician, you will be mainly concerned with the problems involved in the study of exterior ballistics. So this is all the interior, and everything after it leaves the barrel is exterior. At the instant a projectile leaves the muzzle of the gun, it possesses two properties: initial direction and initial velocity. The initial direction is controlled by the gun's elevating and traversing mechanisms. The initial velocity is determined by the interior ballistics of the gun. On the following sheets, you will learn about the factors which affect a projectile's initial velocity. During your study of exterior ballistics a little later, you'll learn how initial velocity affects projectile range. Interior ballistics, as it affects the projectile's velocity, includes the study of combustion of the propelling charge, gas pressures developed within the gun, the speed of the projectile at various points within the gun bore, and erosion, wearing down, of the gun bore. Ooh. Factors affecting projectile initial velocity. One of the most important factors of interior ballistics affecting a projectile's IV, initial velocity, is the rate at which the propelling charge burns. You've already learned the difference between low and high explosives and why low explosives are used for propelling charges. Now let's compare different types of low explosive propelling charges and see how the rate of burning affects projectile IV. All Navy guns use propelling charges instead of cylindrical grains, perforated from end to end with one or more holes. It consists of cylindrical grains. Ooh. This type of charge results in the least muzzle loss, explosive energy wasted after the projectile leaves the muzzle, and highest muzzle or initial velocity for a given charge. A comparison is made below of the effects of different propelling charges consisting of various powder grains upon the velocity of the projectile and the gun bore. The larger, solid projectile grains burn slowest, resulting in the greatest muzzle loss and subsequent lowest IV. The most efficient is the small perforated grain, the fastest burning of the low explosives. Here's a chart, bro. Thus, you have seen the greatest muzzle velocity is obtained by using small perforated grains which have a higher rate of burning. The powder grains of propelling charges designed for use in various guns are not all alike and cannot be used interchangeably. For example, the grains used in 16-inch gun propelling charges are not suitable for use in 20mm gun ammunition. Are you guys all having a good night? You guys enjoying the stream? What are you guys thinking so far? How you feeling? How you holding up? Here's a funny comic. It's been a while since we've seen one of these. How you guys holding up? I'm gonna take a sip. Ah. Give me a second. Posture check. Posture status is checked. Thank you. Just a second. I'm just going to take a short phone break and rest my vocal cords for a minute, because I haven't been talking for a while. As I check Twitter. And other websites. Okay. Two other factors which affect projectile IV in guns using bag ammunition are density and manner of loading. Density of loading is a measure of the amount of propelling charge used to fire a round. The higher the density of loading, the more propellant used. In general, the muzzle velocity increases with an increased density of loading. Manner of loading refers, as the term implies, to the manner in which the propelling charge is placed in the gun breech, and also to the force used to ram the projectile in the gun prior to the propelling charge. If the manner of loading is not kept the same, it will result in variations in muzzle velocity with resultant loss of accuracy. These factors do not affect the IV of projectiles fired in guns using fixed or semi-fixed ammunition. The propelling charges for these guns are fixed, and hence there's no variation in density or manner of loading. The temperature of the propelling charge has a very definite effect on projectile IV. A typical 5-inch gun may have a normal IV of 2500 FPS at a powder temperature of 90 degrees Fahrenheit. A temperature drop of 60 degrees from normal may decrease the IV as much as 100 FPS. That means, like, if the room is cold. So in the Arctic, you're going to get lower IVs generally. Or MVs. When the first round is fired from a gun after it has been cleaned and oiled, the oil film on the surface of the bore slows down the projectile, which must force the oil ahead of it through the tube. This reduction in IV on the first round must be compensated for by proper adjustments to the gun setting, position of gun, and elevation and train. First round. Darn that oil. It slowed me down. Clean bore, normal IV. Ah, a clean bore. Watch my speed. I like this. I'm a big fan of this comic in particular. The causes and effects of erosion. The wearing away of the gun bore during firing is called erosion. Your first guess would probably be that erosion is caused by the friction produced by the rubbing of the rotating band against the bore as the projectile travels through the gun tube, but surprisingly, this is not the case. Some of the causes of erosion are: the surface of the bore becomes intensely heated during firing, and the hot gases rushing across the hot metal scour the surface, as would steel wool. The rapid heating and cooling of the bore during and between rounds tends to weaken the metal, and small surface cracks may develop. Hot gases escaping around the rotating band of the projectile during firing act as high-velocity jets, causing additional scoring and cutting of the bore's surface. So here's a scouring going on. Erosion of the gun bore occurs mainly at the origin of rifling, the point in the gun bore near the breech where the rifling begins. In guns using bag or semi-fixed ammunition, the projectile may be rammed further into the gun, which is the effect of reducing the density of loading, and hence the muzzle velocity is decreased. Erosion also causes the top of the lands of the rifle bore to wear away faster than the bottoms of the grooves, which increases the amount of gas which escapes past the rotating band. This further reduces the pressure behind the projectile and thus decreases muzzle velocity. So as you use a gun more and more, it gets worn out. Exaggerated cross-section of normal and eroded gun bores. And the tops go way before the not tops. Here's another one. You've seen that erosion of the gun bore is due primarily to the high temperature and velocity of the expanding gases during firing, but the alternate heating and cooling of the gun barrel. The longer the hot gases remain in the gun, the greater the erosion. The more time allowed to elapse between rounds, the more the barrel cools, increasing wear due to the change in temperature. Thus, large guns with their longer barrels, which allow the gases to remain in gun longer, suffer more from erosion on each round fired than do small guns. Let's go some more rounds. I'm pooped. Small guns suffer less from erosion on each round that fired than big guns. I like this one a lot too. I'm pooped. Even a slight amount of erosion reduces the muzzle velocity, range, and accuracy of a gun. The gun eventually becomes unserviceable when erosion reduces its effectiveness to a point where the projectiles fired no longer hit the target. Before a gun becomes inaccurate due to erosion, the barrel must be replaced or relined, and guns equipped with removable barrel liners, which is the stuff that goes on here. It's a whole nother thing. Not every gun has that. Darn that oil! The life of a big gun is less in terms of rounds fired than that of a machine gun. A record is kept of the number of rounds fired by each gun, so that proper information of bore erosion can be supplied for fire control purposes, and to enable the gunnery officer to know when the barrel needs replacing. The use of arbitrary ballistics. When the target has been located, its range and bearing determined, interior and exterior ballistics corrections made, and all other details of fire control problem have been worked out, the guns are fired. If all calculations and corrections have been properly made, a hit should be scored. Occasionally, however, it may be noted that the projectiles from one particular gun consistently fall some... Hi, Luciel Kaiser! Welcome! We're reading the second part of like 6 of this manual to fire control for U.S. warships in 1953. It's less of a manual and more of an instructional guide to new people to the field of gunnery. How are you doing tonight? When the target has been... Okay, let's see, I already read that. Despite all the measurements or adjustments made, no cause can be determined for the consistent error of the gun. In such a case, a correction is applied to the gun settings to compensate for the consistent error. And this correction is called an arbitrary ballistic. Welcome to the stream tonight. Enjoy the beats and me reading. 67-year-old document? 68? It's a long time. So, stuff is just going to end up consistently going short sometimes. And so you just kind of just pump the numbers up and then it works. Pretty simple. The need for and the amount of arbitrary ballistic correction is quite new for me. Going to be interesting. Yeah, it's this is cutting out the math for the most part. If there's a math section, I'm going to skip it. But it's mostly just informative. And if there's stuff that you missed, you can go back to the VOD later and listen if you want. It's good content, I think. I think the music might not be there if I set up OBS right. But the need for and the amount of arbitrary ballistic correction can be determined only by the observing the fall of a great many rounds. The fact that 1 or 2 rounds fall short or beyond is not justification for application of an arbitrary ballistic. A careful study of all the factors of the fire control problem must be made before it is decided to use an arbitrary ballistic. Interior and exterior ballistics. On the preceding sheets, you learned about guns and their construction, gun mounts, and types and characteristics of explosives. You also learned about various types of ammunition and projectiles. Finally, you studied the meaning of interior ballistics and learned about the factors which... You don't hear music, actually? Did I mess it up? Oh no, is it quiet? You hear it now? I might have had it too quiet. I didn't know if it was too quiet. Is it here now? It's just a little bit quiet. Okay, I wasn't sure how loud to make it. The OBS thing, I know decibels are like they're a magnitude thing. They're logarithmic, but the audio mixture makes me want to keep it lower. But this is probably good here. First, finally study the meaning of interior ballistics and learn about the factors which affect a projectile during its travel through the gun bore. Now you should have a pretty good idea of what is required to start a projectile on its trip to the target. You have the gun properly mounted and loaded with a complete round of ammunition. The propelling charge is ignited, the projectile travels through the barrel under the influence of the interior ballistics factors and emerges from the gun barrel traveling at a fixed speed and in a certain direction. What then? I'm going to read this little comic in a second. Let me take a sip. I got some dry ass lips. Let me do this so I can see my chat. Start raining. Exterior ballistics. I'm out of the gun, according to plan. Now what? Initial speed and direction, bore erosion, propelling charge and burning rate, powder temperature, and density and manner of loading make up interior ballistics. You get a thumb crack? Okay. Do some other fingers. Right in the mic. some Sorrel finger crack ASMR. Why don't you? At the instant the projectile leaves the gun, its initial velocity and direction are fixed, and the influence of the interior ballistics of the weapon is ended. The course which the projectile follows after leaving the gun muzzle is determined by exterior ballistics. Thus, interior and exterior ballistics are related by projectile initial speed and direction. In the next section, you will study exterior ballistics, analysis of the factors which affect the projectile during its flight from gun muzzle to target. This is very long. This beautiful diagram. The problem of exterior ballistics. Exterior ballistics involves an analysis of the forces which act on the projectile and affect its course during flight from gun muzzle to target. Exterior ballistics is also concerned with the practical problem of flying a gun, setting it in elevation and train, to incorporate ballistic corrections and enable a projectile fired from it to hit the target. The discussion in this section will be limited to the factors involved in solving the problem of hitting a fixed target from a fixed position, no relative motion between gun and target. If there were no forces acting on a projectile during its flight to the target, fire control would be a simple manner. All that would be necessary to score a hit on a fixed target from a fixed position would be to aim the gun directly at the target and fire. When a projectile is fired from a gun, its momentum, resulting from the projectile muzzle velocity, tries to keep it on course in line with the gun bore. Many forces act on it, however, before it reaches the target. The Earth's gravity pulls it down. Air resistance, due to the friction of the projectile pushing through the air, slows it down. Wind and air currents force the projectile off its original course, and the spinning of the projectile tends to make it drift off course. All these factors greatly alter the projectile's course and must be considered when determining how to elevate and train the gun in order to score a hit. You will learn in the next few shoots about the effect of each of these forces. This is what would happen if there was no forces on the shell after it's fired. I'm just going in a straight line like a laser beam. Analysis of the vacuum trajectory. If it were possible to remove all the air from around the gun and the target, the only force which would act when a projectile fired into the resulting vacuum would be the downward pull of gravity. If the gun were aimed perfectly horizontal and a projectile fired at the same instant that of an identical projectile was dropped vertically from the level of the gun muzzle, both projectiles would hit the gun at exactly the same instant. This is true in a vacuum, because gravity is the same regardless. It's kind of crazy. It's like when you if you drop a feather in a vacuum, it falls at the same speed as a brick. Test it out. Get a vacuum box thing and drop a feather and then drop a brick. Fall at the same time. Give me a second to check Discord. Who dares at me on Discord? Okay. This illustrates that the force exerted on a projectile by gravity is always the same for a given projectile, regardless of its speed or direction of travel. If the guns were pointed up at some angle and a projectile fired, its initial velocity could be resolved into horizontal and vertical components. There is no opposition offered in a vacuum to the horizontal velocity component, so this remains constant during the projectile's flight. Gravity, however, exerts a constant downward force, which opposes the vertical velocity component. There's stuff going on here. As the projectile continues its flight from gun to target, gravity continues to oppose and reduce the vertical velocity of the projectile until it becomes zero at the midpoint of the flight. From this point onward, gravity causes the projectile to attain a downward vertical velocity, which continues to increase until the projectile hits the target. This is math you've probably done in high school, in like Algebra 1. You did this math. This is algebra. Now, once you include stuff like air resistance, it becomes physics. But until then, it's just algebra because it's just like x. For x is distance. No, x is time. Yeah, I don't remember the formula, but it's like I forget the formula. I'm sorry, I'm not a math guy. At the midpoint, 0. Therefore, since the force exerted by gravity is constant, the downward velocity towards due to gravity attained by the projectile when it reaches the target will equal the vertical component of the muzzle velocity. The total velocity of the projectile when it strikes the target then will equal the initial velocity, since the horizontal component has not changed during the projectile's flight. Again, this is where just gravity is involved in a vacuum. The trajectory of a projectile fired in a vacuum has a regular curved shape as shown below. The projectile reaches its highest point of travel at a midway point between gun and target. Again, vacuum. Some line of fire, line of fall. Yeah, you get it. The projectile leaves the gun along the line of departure and approaches the target along the line of fall. These lines make equal angles with the horizontal, so that the angle of departure equals the angle of fall. In the case illustrated, when the gun and target are the same level, the line of sight from gun to target is horizontal. You saw from the projectile velocity analysis on the preceding sheet that the velocity of the projectile when it strikes the target equals its initial velocity and leaves the gun muzzle. It is not possible, of course, to create a vacuum between gun and target. If you can do this, you're scary. But if you understand the vacuum trajectory, it will be easier for you to understand the effects of a projectile's trajectory on air resistance, wind, and projectile spin. The effect of gravity on a projectile's course of flight is constant in a vacuum and or in air, and if it were the only factor to consider, fire control would still be a simple problem. It is primarily the other exterior ballistics factors which require elaborate consideration before the fire control problem can be solved. The initial velocity and direction of a projectile determine where it will fall. These are the only properties which can be imparted to a projectile by a gun, and if they could not be controlled, the gunner would have no control of his weapons. Once the projectile has left the gun, he can't tell it where to go. It is vitally important, then, that we know exactly how a projectile will travel after it leaves the gun at a known speed and in a known direction, so that we can adjust these factors as necessary to make the projectile hit a target. If a projectile is fired at a fixed elevation angle in a vacuum and the initial velocity is varied, the range will increase as the initial velocity increases. Since the vertical component of the velocity is larger, it takes longer for the constant force of gravity to overcome the projectile's upward travel. This allows the horizontal velocity component to carry the projectile farther from the gun, resulting in increased range. That's true. In guns using bag ammunition, it's possible to change the initial velocity by using larger or smaller propelling charges. Certain fixed ammunition intended for beach bombardment use a special low initial velocity powder for the propelling charge. In guns using fixed ammunition, however, no control of range is possible by varying initial velocity, since the initial velocity of such guns is fixed for a certain gun using given ammunition. How elevation affects range. If a projectile is fired in a vacuum with fixed initial velocity, its range will depend only on the elevation angle, the angle between the gun bore and the horizontal. As I don't remember what EG means. Increase from 0, I guess elevation, from 0 to 45 degrees. The range increases since it takes longer for gravity to overcome the vertical velocity, and during this time, the projectile travels further from the gun. As the vertical velocity increases due to increased elevation, the horizontal velocity decreases. As the gun is elevated higher than 45 degrees, the time the projectile is traveling continues to increase, but the horizontal velocity will be so reduced that even in the longer time, the projectile won't go as far. You can see that for any range, there are two possible elevation angles, one greater and one less than 45 degrees. To keep the time of flight to a minimum, elevations less than 45 degrees are used for fire against surface targets. Elevations greater than 45 degrees are typically used only for anti-aircraft fire. So here we go for this is the hell segment. As a projectile travels through the air is forced out of the projectile's path, just as a ship forces the water from in front of it as it moves from the sea. As the air is moved aside, it exerts a force on the projectile which opposes its motion. This is like Newton's first law, bro. Here's a little man stopping the bullet. He's strong, bro. Look how strong that guy is. Stopping such a big bullet. Just as the force of gravity opposes the vertical component of projectile velocity, the force due to air resistance always acts in opposition to the total velocity of the projectile, sum of vertical and horizontal components. air resistance varies depending on projectile size and projectile velocity. I think this will also be the last sheet I read. We'll do the rest another time, I think. But this is long. The faster a projectile moves through the air, the faster it must force the air out of its path. The more rapidly the air is moved out of its original position, the greater the force it exerts on the projectile. Thus, air resistance has a greater effect on projectiles traveling at high velocities than it does on slow-moving projectiles. As long as the projectile is in flight, air resistance continues to reduce its velocity. Thus, the projectile travels much more slowly as it approaches the target than it did when it left the gun muzzle. Also, the longer projectile remains in flight, the more slowly it travels, which results in a shortening of the trajectory at the far end and a great reduction in range as shown below. The trajectory high point is no longer the midpoint as it was in a vacuum, but will be nearer the point of impact than it is to the gun. The angle of fall is greater than the angle of departure, and the striking velocity is less than the initial velocity. Which, this is logic there. Makes sense, right? You guys are following this? Pain Eras, son of a gun. Any projectile, ooh, my finger, fired in a vacuum at an elevation of 40 degrees and with an immune, I don't know why I see immune, initial velocity of 2500 FPS will attain a horizontal range of 192,000 yards, almost 100 miles. At the same elevation in the air, a 16-inch projectile will attain a range of only 42,000 yards, a 5-inch projectile 17,000 yards, and a 1.1-inch projectile only 7,000 yards. The illustration shows how a projectile size radically affects its range in air. Large projectiles have more initial energy and will travel farther against air resistance. This is because of inertia. The more mass you have, the more it takes to slow you down. Because of air resistance, maximum projectile range is not attained when the elevation angle equals 45 degrees, as is true in a vacuum. In air, maximum range occurs when the elevation angle is slightly more or less than 45 degrees, depending on the characteristics of the gun and the projectile. For instance, the maximum range of the 5-inch gun is attained when the angle is 45 degrees, 35 minutes, just a little less than 45 degrees. A minute is a 60th of a degree, if I do recall. You can see the presence of air greatly complicates the fire control problem, and that careful adjustments are required to compensate for its effects. Why projectiles drift? You learn when you studied gun construction that the bores of Navy guns are rifled by cutting a series of twisted grooves on their interior surfaces. You also learned in the section which dealt with ammunition projectiles that projectiles are provided with a rotating band, which engages the rifling of the bore and gives the projectile spinning motion as it travels through the bore. Now let's see why it's necessary that projectiles spin during flight and what the effects of the spinning motion are. As a projectile travels through the air, its spinning action makes it behave very much like a spinning top or hoop, or a football. That is, it tends to resist any force that tries to change the position of the axis about which it is spinning. This tendency on the part of a rapidly spinning object is known as gyroscopic action. In the case of the spinning projectile, gyroscopic action tends to keep the projectile on course, making it possible to predict the course of the missile and hence achieve accuracy of fire. If the projectile did not spin, it would tumble or wobble during its flight and would not maintain a predictable course, making accurate fire control impossible. Smoothbore isn't bad necessarily. There are instances where smoothbore is good, but that's not relevant here. Usually tanks have smoothbore, I believe, nowadays. During its flight, the spinning projectile attempts to align with its axis with the spin with the tangent. We're getting to tangents, we're getting into math, oh no! The projectile's trajectory. Since the trajectory is curved downward, the nose of the projectile must move down as the projectile moves forward. This downward motion of the projectile's nose is opposed by air resistance, as is the projectile's forward velocity. Thus, an upward force, I'm losing it, is exerted on the projectile's forward end. Suppose now that we consider one point on the surface of the projectile in flight. It has a velocity AB. Okay, let's just. let's just... Here's a comic. This is good. If you've ever played football on a windy day, American football, you are familiar with the effects of wind on an object in flight. Depending on the wind direction and velocity, your well-aimed forward pass may have curved to the left or right, fallen short or beyond the point where you wanted it to land. Wind has exactly the same effect on a projectile in flight. If the wind blows from the left, the projectile's trajectory will turn to the right and vice versa. If the projectile is headed into the wind, its range will be decreased, and if it travels with the wind, the range will be increased. You can see that the effects of wind must be considered in the solution of the fire control problem. So there you go. That's what various types of wind do. If the wind is blowing at right angles to the projectile's line of fire, it is called a crosswind. If it is blowing along the line of fire, either with or against the projectile, it is called a range wind. Corrections for crosswind are made to the train angle separately from those for drift. Range wind is compensated for by increasing or decreasing the elevation. The effects of crosswind and range wind continued. If the wind were cooperative enough to blow at all times either in line with or at right angles to the projectile's line of fire, it would be a relatively simple matter to compute the corrections required when the wind velocity is known. Usually, however, the wind blows at some angle to the LOF, line of fire. In order to correct for range and crosswinds, it is necessary to resolve the true wind into components in line with the perpendicular line to the line of fire. When this is done, each component can be treated individually and the proper gun setting adjustments made. Just fix it, bro. When the projectile is first fired, it is traveling at such a high speed that the wind does not affect its flight very much. As it slows down during its flight, the wind affects its course more and more because of how inertia works. The faster and the more mass you have, the harder it is to stop you. Hence, the longer projectile remains in flight, the more its course will be altered by the winds, so that wind deflection increases with range. Two other factors that affect the amount the projectile deflects are wind speed and projectile size. The napkin monologue from SPR. Okay, give me a second. Let me pull that up. Let me hide Vivaldi. Of course, Nezu. How you doing tonight? The stream is kind of nearing the end once I finish the very long page that I'm reading. Give me just a second. I will turn off the music for a second for reading this. Should I put on Valentine's theme? Actually. Fan-made. I don't want a fan-made theme. I want the... Yeah, baby. How loud is that? Is that good loudness? Turn it down. This from Eyes of Heaven. Is that volume good? Is that too loud? Have I ever heard about USS Texas? I have. I have not been there. I'm from Maryland, so I've not been to Texas in my life. Holy Pepe Jammer? Yeah, this is a good track. I would have been playing these most of the time, but I'm going to just do that for this reading. But I'm going to start right now, fellas. I'm going to restart the music. Suppose that you were sitting down at this table. The napkins are in front of you. Which napkin would you take? The one on your left or the one on your right? The one on your left side or the one on your right side? Usually, you would take the one on your left side. That is correct too, but in a larger sense on society, that is wrong. Perhaps I could even substitute society with the universe. The correct answer is that it is determined by the one who takes his or her own napkin first. Yes. If the first one takes the napkin to the right, then there's no choice but for others to also take the right napkin. The same goes for the left. Everyone else will take their napkin to the left because they have no other option. This is society. Who are the ones that determine the price of land first? There must have been someone who determined the value of money first. The size of the rails on the train track, the magnitude of electricity, laws and regulations. Who was the first to determine these things? Did we do it all? Did we all do it because this is a republic, or was it arbitrary? No! The one who took the napkin first determined all of these things. The rules of this world are determined by that same principle of right or left. In a society like this, table, a state of equilibrium. Once one makes the first move, everyone must follow. In every era, this world has been operating by this napkin principle, and the one who takes the napkin first must be someone who is respected by all. It's not that anyone can fulfill this rule. Those that are despotic or unworthy will be scorned, and those that are losers, and those are the losers. In the case of this table, the eldest, or the master of the party, will take the napkin first, because everyone respects those individuals. Loud AF? I'm sorry, could you still hear me good? The standard width of the railroad track was set to fit the average size of the Roman road. Oh, in which country? Doesn't that differ by country? Whoa! Thank you so much, Nezu. I'm gonna have to get another emote made. In England. Ah, gotcha. Gotcha, Pina. Thank you so much. We're at 29 points now, so I gotta make a new emote. Or commission one, it seems. I'm sorry it was so loud. I don't get how this works. Thank you for the follow, John the Firecat. Thank you, homie. This is from part 7 of JoJo, Steel Ball Run. I hope it wasn't too loud. In the VOD, it might not be there if I did the setting right, but I don't think I did the setting right, but we'll see. Let's put back up Vivaldi. Here I just had the script pulled up. See the meaning on this fake genius website. The point of this entire speech is that no matter what you do, if you're in a position of power and act first, everyone will act accordingly and act that way. It's not strictly wrong. Once a standard is set, all must follow. That's basically what he's saying there. And that he wants to set the standard for the world. That's what Funny Valentine's ambition is. Read Steel Ball Run. That is all. I'm excited to buy the paper version in 10 years. So wind higher up moves differently from wind lower below? But thank you so much for the gift subs, and thank you for the follow. We have 29 subs on this channel right now. That's scary.